welcome again. So today's lesson will be on the Chemical Earth module in Year 11 Chemistry. And in this series we're going to look at formulae for compounds. Okay, so what this series will focus on is how do we name compounds and how do we write out their chemical equations or chemical formula or formulae for in order to sort of compact the way we represent chemicals. Okay, and this is an important skill because the way that we write formulae for compounds is standardized across every country. So you'll be able to communicate with chemists in other countries just by knowing this standardized way of writing these formula. Okay? So chemical compound formulae. Okay, so we're going to look at how we actually write chemical formulae and how we actually represent chemicals using their chemical symbols and other numbers and things like that. Okay. So the basics of chemical formulae. Correctly representing these chemical compounds with a formula is an important skill. Okay, so using a formula to represent a chemical is a skill that all chemists need to know, otherwise you won't be able to communicate with other chemists. Now what this requires, in order to learn this skill, you have to have learned your valencies very well. Okay? So when I was in high school, my chemistry teacher always stressed how much we had to remember our valencies, and this is why it's important, because if you don't know your valencies, you'll never be able to get the right formula for the right chemical. Okay? So this sentence is of key importance to you guys. Okay? So remembering that we have ionic, covalent, metallic structures and all these other things, we're going to just focus on each section in order to better understand how to write chemical formula for one section. So we're going to look at how to write an ionic formula first, and then we'll look at covalent ones later. Okay? So firstly, you have to identify what the component elements are. Okay? So if yellow was, say, chlorine, and green was, say, sodium, they should actually be the other way around, but anyway, let's just go with that, just for argument's sake. Then we need to know what's there. So we know that it's chlorine and sodium. Okay, so that's the first step. Okay, just identifying what we actually have in this, in the actual compound. So it's the easy one. Then you have to determine the valency of each component. Okay, and we know we can do this using the periodic table, or if your memory is really good, maybe your teacher has given you a table of valencies and you just remembered them all. Okay, so you can use the periodic table, but some of those polyatomic ions like carbonate or nitrate, you'll have to just remember off by heart. Okay? Okay, so then we multiply the number of components so that the final compound is electrically neutral. Okay, so this is a complicated one, and it of course doesn't make a lot of sense right now, but basically your ionic compound will be electrically neutral from far away. So if I was to hold a piece of salt and look at it, I would see it as an electrically neutral piece of salt. Okay, so if I brought, like, for instance, just say some very positively charged wire near my salt in my hand, then you wouldn't see like the salt moving because it doesn't react to that electricity. That's what we mean by electrically neutral. And I'll explain how we get this part when we go through the example. But all we have to know for now is that we have to make sure that this unit here, our formula unit, is electrically neutral. Okay, we can't have a charged formula unit, otherwise that doesn't make sense. Okay? So here's our example. Magnesium, which is Mg, hopefully you know this, and chlorine are reacted together. So you react these two things together. Determine the chemical formula of the resulting ionic compound and write a balanced equation for this reaction. Okay? Fairly standard question. So first, okay, we've already identified, so we don't really have to worry about that now because we know it's magnesium and chlorine. So we'll determine the valencies first. So if you look up the periodic table, you'll see in group 2, magnesium is there. So you know magnesium has a valency of +2. Okay? And if you're looking for chlorine, it's in group 7, so you know that chlorine has a valency of -1. Okay, so we should remember this from all our study of the periodic table so far. Okay, and the final form of the compound is magnesium with some number of magnesium atoms and some number of chlorine atoms combined together. Okay, and we need to figure out what X and Y are. So is it Mg2Cl1, or is it Mg5Cl50, or is it, MgCl, just 1 and 1? That's our job to figure this out. And that electrically neutral part is how we'll work this out. Okay. And magnesium is written first simply because it's the metal. So you write, so the one that comes first is the one on the left-hand side, and the one that comes second is furthest to the right-hand side of the periodic table. Okay. Okay, so to work out X and Y, we find the lowest common multiple of the charges in terms of absolute value. So don't worry about the signs. So if, for instance, chlorine is -1, but we're just going to say 1 at this point. Okay. And then multiply the charges by the appropriate number to achieve that value. Okay, so we've got, so the lowest common multiple, we had magnesium has a valency of 2, and chlorine has a valency of 1, or -1, but we're taking the absolute value, so it's just 1. And so the lowest common multiple is 2. Okay? So for magnesium to have a charge of 2, it's just charge times X equals 2. So obviously the charge is 2, so X equals 1. Okay? So we know the charge is 2, and X has to be 1 in order for that to equal 2. Okay? Now similarly for Y, you've got the charge of the chlorine ion times however many chlorine ions per molecule, or per unit, to give you 2. So you've got a charge of 1. Then to get to 2, you need Y to be equal to 2. So Y equals 2. Therefore, the final form is magnesium 1, chlorine 2, so MgCl2. Okay? And you can see that if we have this Mg2 plus and Cl minus, if we were just to put them together straight away, you would have MgCl plus. You see the charges don't go to 0. And that's why we needed 2 Cl ions for every 1 Mg ion. Okay, so you can see that from the electrically neutral point of view. Okay, and the final equation then would be MgCl2, remembering that chlorine exists as a diatomic gas. That goes straight to MgCl2. Okay. Now we've just done ionic formulas, or formulae. And so we're going to talk about covalent molecular formulae now as well. So the procedure for developing these formulae is the same as for the ionic case. So the way we do it is very similar. The only difference is that you don't need to worry so much about the charge, and we'll go through that as we go. The more difficult aspect of this naming convention and writing covalent formulae is naming the compounds correctly. Okay, so there's a big, so the process is exactly the same. You make an electrically neutral compound, but the difficulty becomes actually naming the compound. So there we have our issue. Okay, so naming covalent molecular compounds is what we're going to focus on. So just remember the process is exactly the same as the ionic process. Okay, so you use the normal element name for the leftmost element on the periodic table. So if we were to deal with, say, why don't we go with carbon dioxide, okay, CO2. We know that's a covalent molecular compound. So you can see carbon is here, and oxygen is here. And you can see carbon is further to the left than oxygen. So we just use that part, its name, as the first part of our compound name. So we have carbon here. So the leftmost, you use the normal element name for the leftmost element on the periodic table, and an "-ide" suffix for the other element. Okay, so the other element is oxygen, but instead of writing oxygen, we drop the "-igen" part, and we give it an "-ide" suffix. So it becomes oxide, right? And because there's 2, we write di meaning 2. And you can see that that's our carbon dioxide, which we're all very familiar with. Okay, so that's an example of how we name covalent compounds. Now, the question then becomes, oh, well, what happens if, you've got oxygen and sulfur together in, say, sulfur dioxide? Which one do we put first? Okay. Well, the one you put first is the one lower down in the group. So you can see sulfur is here, and oxygen is here. So sulfur is below oxygen, so it comes first. So it becomes sulfur. And then obviously the "ide" stuff comes up after, oxide. And there's two, so it's di. Sulfur dioxide, right? And there it is there. Okay, so if they're in the same group, it's the one that starts is the one lower down in the group. Okay? Now, an exception to this rule, to the rules, is that oxygen is named last in compounds with Cl, Br, or I in them. So for instance, Cl2O is actually shouldn't be oxygen chloride or oxygen dichloride. It's actually always oxide is last. Okay, so pretty much in all cases, yeah, oxygen will be last. Okay, so oxygen is always the last chemical you write. So this one is actually chlorine monoxide, not oxygen dichloride. Okay, so this one here. Even though chlorine is further to the right than oxygen, this exception sort of gives you a little bit of leeway there. Okay. Now the number of atoms of each type is given by using the prefix mono, di, tri, tetra, penta, or pent, depending on the situation. Hexa, hepta, octa, and all those other all the rest, surely, in front of each part of the name. So carbon dioxide, there were 2 oxygens for every 1 carbon. So we use di as the prefix, so it's carbon dioxide. Okay. Now if it was, for instance, SO3, we would use sulfur. 3 is tri, so sulfur trioxide. Okay, so that's just how we name different chemicals. Okay, so that concludes today's lesson on the basics of chemical formulae. We've looked at ionic chemical formulae and covalent chemical formulae, and how we develop them, how we figure out what is the actual chemical formulae or formula for that particular compound, and how we name it as well. Okay, so hopefully in the question segment we'll get more practice at doing these, or at least learning how to do these, and you'll hopefully learn on your own how to get these equations or formulae, and how to write the chemical names. Okay. So what is the formula for potassium nitrate? Okay, so potassium is K, nitrate is NO3. This one you should remember, this one you can look up. And if you look on, this is group 1 here, potassium happens to be in group 1. So it's got a 1+ valence. And if you remember, nitrate has a 1- valency. Now, if you take the lowest common multiple, it's 1. Therefore, it'll just be KNO3, because they're both 1, and the lowest common multiple is 1, so it's just KNO3. And if you look at it, if you've got the K ion and the NO3 ion, if you put them together, the charge balances out. You get 0. 1 minus 1 gives you zip, 0. Okay? What is the formula for aluminium sulfate? So if you look in your periodic table, you've got aluminium as Al, and you've got to remember sulfate from your list of valencies. And aluminium is in group 3, so it's got a valency of +3. And sulfate, as you should remember, has a valency of 2-. And now we have it. Okay? Now, if you take the absolute value of each, the lowest common multiple is 6. 3 times 2, which is 6. Okay? So therefore, for aluminium, you need the charge of aluminium times 2, which equals 6. So, sorry, you need, because of the valency, to get 6, you need to multiply the number of aluminiums by 2. And for SO4, you need to multiply by 3, and you'll get 6. And so you'll have, for every molecule of aluminium sulfate, you'll have 2 aluminium atoms and 3 sulfate ions. Okay? So that's how we do that. And what is the valency of M in the compound MO4 2-? So this sort of permanganate ion, what is the valency of M? Okay? So if we go in our periodic table, the valency of oxygen is usually 2-. Okay? And if there are 4 of them, the valence or the charge of 4 oxygen atoms becomes -8. Okay? Now, if the ion has an overall charge of 2-, then the valence of M must add with the valence of O4 to equal 2-, right? So if you've got 8 negative charges, and in total, what you can see from the outside is 2 negative charges, there has to be some number of positive charges cancelling out some of these negative charges. Okay? So the valence M plus the valence O4 has to equal 2-. So the valence M plus 8- equals 2-. And so the valence of M must be 6, okay? Plus 6. So let's have a look. M plus 6, O4 -8, and if you do the maths, you'll get -2, okay? And that's how you work it out. Write down the formula for dinitrogen pentoxide. Okay, so this is quite a complex one, but you just break it down into steps. Di is 2, fairly straightforward. So dinitrogen is N2. Okay, so di is 2, dinitrogen would be N2. Now, obviously by the same logic, pent is 5, oxide is O, so it's O5. Okay, and so you put them together now, and you get N2O5. Okay, so it's very straightforward, and it all comes from the name. You can see it straight away. And that's the beauty of this chemical naming convention, that everything you need to know is already in the name. So what does the chemical formula represent for a covalent network substance, and why is it written this way? So we did a lot on covalent molecular substances, CO2, O2, H2O, all of these things. But they exist as discrete molecules. So, you know, a carbon dioxide molecule could be flying around by itself, and another carbon dioxide molecule could be going by itself in any direction that you want, and so they're not interacting with each other in any way. But in a covalent network substance, like silicon dioxide, they're actually all interlinked together. So then, how do you write that chemical equation? Do I write, for instance, for 1 mole of silicon dioxide, do I write, you know, Si 6.022 times 10 to the 23 O, you know, 12.044 times 10 to the 23? Okay, like that's essentially the same thing as what we were writing before, the number of molecules and things inside. But is this a really clever way of doing it, or is it just tedious? And in my opinion, it's really tedious. You can't write that and expect everyone to know what you're talking about. So the way we write it is, the chemical formula of a covalent network substance is the smallest repeating unit of the covalent network structure. And what I mean by a repeating unit is, you know, if there's a silicon and then an oxygen and then a silicon and then another oxygen, then silicon and oxygen is the repeating unit. So that's what we write, SiO. Okay? Similar to ionic compounds, it is essentially the empirical formula for the substance. So in ionic compounds, the same thing happens. You get sodium, then chlorine, then sodium, then chlorine, then sodium. So you just write sodium and chlorine together, rather than writing a billion different Na and Cl. You just write one. So it's the same thing with covalent network structures. This formula is used because the crystal will likely have an innumerable amount of atoms. and it would be impractical to write all of them, particularly if they have a repeating pattern. So it'd be silly to write like, a billion different chemicals, or a billion of the same chemical over and over and over again, simply to represent a repeating pattern anyway. So we just write it as a single repeating unit, and that's all. And that tells chemists everything they need to know. So there's like an implied convention there. So that's why we write covalent network structures the way we do. So that wraps up today's lesson on formulae for compounds. So we actually looked at how we write formulae and how we name chemical compounds. So in future lessons, we'll be looking at other ways of identifying compounds. And so I look forward to seeing you at our next lesson.